One of my favorite writers, a man named Edward Abbey, states that growth for the sake of growth is the ideology of the cancer cell. While I didn't expect to find the ideas of a radical environmentalist influential to my summer E-STAR project, sure enough, I found echoes of this idea in my project as well as in the current state of science in America. But before I get into all that, let me give you a little background on my research. The first term you need to understand is chiral. Chiral basically means that a 3D object cannot be superimposed upon its mirror image. The most common example of this is our hands, because no matter how you divide your hand, there's no axis of symmetry. It has no point of symmetry. In my project, I attempted to make chiral microparticles. I made these at 2.5, 5, and 10 microns in diameter. For reference, a human hair is around 100 microns thick, so these were so small that you couldn't even see a clump of them without a microscope. The ones over there are chiral because they're kite-shaped and they have no axis of symmetry, while the ones here I would call achiral because they're just straight-up pyramids. The main property that chiral materials exhibit is something called circular dichroism. This basically means that they absorb light differently based on if they're left-handed or right-handed particles. You might have heard of light as moving as a wave, but light is also circularly polarized, meaning it spins either to the left or to the right. So it seems weird, but when you have these chiral particles in solution, they'll absorb left-handed circularly polarized light and right circularly polarized light differently based on the particle's handedness. Just like how they interact with light, chiral materials also exhibit interesting effects when a magnetic field is applied. When a magnetic field is applied, they will spin to the right or to the left based on their handedness. So we were seeking, in terms of applications, we were hoping that this could be used to create nanotechnologies, like braiding ropes at the nanoscale. We were even thinking it could be used in imaging, like imaging complex tissues in the body based on how these particles move through tissues and how they move through different fluids when a magnetic field is applied. I did my research at LSU's CAMD facility, which is it's kind of by Whole Foods. You might have seen it before. And it was built in the 80s as this pinnacle, this cutting-edge technology facility. And it has all these crazy technologies, and it was really at the forefront of science 30 years ago. Now it's a little more derelict. You can see just exposed wires everywhere. It's a little older, a little underfunded, but it has a certain charm to it. The area I was working in was closed off and had this diffused orange lighting. A lot of the machines I was using were actually 20 to 30 years old, which means they were a lot older than me. The sector I was working in was called a clean room, meaning that they scrubbed the air for all dust and particulates. So I had to wear this funny suit and these gloves and this hairnet because any amount of particulates like skin oil or dust or hair getting on the project will actually mess it up because any small imperfection can be catastrophic. What's most important in my project was actually drawing the initial shape of these particles. So to do this, I used a technology called e-beam lithography, and specifically a microwriter. So this microwriter MLC focuses an electron beam through very precise lenses, and it's able to draw an array of billions of these microparticles onto a small silicon wafer within around 30 minutes. So the way I actually made these particles was by etching pits in silicon wafers in the shape of a particle. So I started with a silicon wafer coated with silicon nitride, and then finally with photoresist on the top. This photoresist on top is very important. The photoresist is a light-sensitive polymer, meaning that when it interacts with light, in this case the e-beam lithography, the electron beam from the e-beam lithography, it becomes weakened, and it's able to be dissolved by a chemical called developer. So once I immersed the wafer, after going through e-beam lithography in this developer, it left a hole in the shape of the particle that I wanted. I then proceeded with reactive ion etching to get through the silicon nitride, and then I used KOH etching, potassium hydroxide, which is a strong base, to etch into the crystal planes of the silicon, and I'm left with a pit in the shape of the particle that I want. After this was actually creating the particle. To do this, I inverted the wafer and then evaporated gold into the pits. So gold is typically a solid at room temperature, as you all know, so it requires an extreme amount of heat through an electron beam to actually turn this solid gold into a vapor. So I evaporated it and it deposited in the pits to make the particle. I then removed the excess gold and then did a layer of silver to help removal later on. So this is me holding a wafer that I just got out of the machine. It had a thin layer of gold deposited as a film across the whole surface of it. So after this, I had to actually extract the particles. So I did this by gluing them to a glass slide with a UV curing superglue, and then actually separating the two. And because they're glued to this glass slide, they'd stay on the glass slide, and then I'm left with a glass slide with millions of these particles mounted tip up. I then used various chemicals to dissolve the silver and dissolve the glue until I was left with these particles in solution. So I was able to make achiral microparticles, which are just the straight up pyramids. I was able to make those from gold and nickel, but unfortunately I was never quite able to make the chiral ones. So this is because this is the photoresist, as you can see here, and these shapes are really blobby. They wouldn't exhibit high circular vectorism, and they're just not what we're looking for in the project. So I wasn't able to actually call that a success. So I was initially frustrated because this project I had spent months working on over the summer didn't really work. I wondered why we were even doing it in the first place, because my professor told me that 10 years before, he was able to make chiral microparticles using similar techniques, but with older technology. When I talked to my graduate student, Michaela, who was advising me, she said that the main reason we were doing this project was to sort of beef up the resumes of a lot of the lab technicians there. I was confused by this, why we were doing it if we'd done it before. I wanted to see if this illustrated some larger trend in American science, and sure enough it did. While over the last 40 years, the amount of research funding has steadily increased, the amount of major discoveries being made in America relative to the rest of the world has actually declined. And a study from the University of Oxford estimates that $200 billion annually are wasted on unnecessary studies. These studies and projects have either already been done before or have poorly designed parameters. This is because the system of grants in America selects for the projects, not the projects that are the most ambitious or the most revolutionary, but the projects that are guaranteed to get results. Because of this, you'll see a lot of projects get funded that are simply recycling or barely changing old research, and that's not actually leading to any innovation. Well, you might think, well, we should do it multiple times to repeat it. And sort of confirm that it works. It's assumed of career academics that when they're actually making a technology like these microparticles, they'll have done it multiple times before publishing their paper. So we don't need to do this over and over again over a period of 10 years or more just to prove it works. We already know it works. I'll give you an example for my project. These are all papers I found while doing background research. So you can see they all have similar titles, and they actually have basically the same content. They're published from a wide variety of years, but they all say the same thing. They all preach about the broad interdisciplinary applications of chiral microparticles. Yet after 10 years, it has not been applied to anything outside of its field of origin. Like Edward Abbey said earlier, this method of science is inefficient because it just bloats itself based on previous research and does not generate anything new. So what conditions will generate innovation? Well, the historian Jared Diamond thinks that certain environmental conditions present in a society, or in our case a lab, can actually determine if it will be innovative or not. First, he says that a society or a lab must combine existing technologies to create new discoveries. And second, and most important, is that that new discovery gives the group a competitive advantage over those around them. The system of grants, as it is, does not follow these two. I'll give you two examples from world history that illustrate this. First is the region that now makes up modern China. From late antiquity to the early modern period, this region was ruled by one political authority, meaning that they had no real incentive to innovate because they had no meaningful competition for their neighbors, and it was just one stagnant political authority. In contrast, Europe during the Middle Ages was politically fragmented. So all these states competed for land, they competed for power, and they competed for influence and trade. And through wars and contests of expansion, this resulted in numerous technologies being made during the Renaissance, like the astrolabe for navigation, the printing press to spread more ideas, and even early forms of water power. All of this was done before we even really understood the solar system. So without resorting to wars and contests of imperialism like what happened in world history, how can we actually apply this to science and generate better results through innovation? I say that there needs to be more job security for career researchers. PhD students and professors need to have more tenure so they're able to pursue risky projects without jeopardizing their job security, because when they have to keep getting grants, they just recycle old research. There also needs to be major rewards in terms, that's mostly just a lot of money if they get a good discovery, because that money can be reinvested into a lab and make sure that lab continues to innovate. Finally, and most importantly, it needs to be interdisciplinary. Most major inventions were not sort of created in the field they originated in. Chiral microparticles can be applied to fluidics, they can be applied to optics. Some people even think that it can be applied to biochemistry. To actually achieve innovation, technologies need to expand past the field they originated in. I encourage all of you to engage with science in some sort of way, either through the eStar program, through independent research, or not, because a lot of the discoveries that are currently changing the world, you have to be scientifically literate to know what's going on. In my research, I learned a lot about what I value in a job, and I also learned how to sort of understand how science even works. You can see here, I'm solving a problem about photoresist thickness. I had to work with all these old machines and figure out the thickness of a layer, and then see how to thin down my photoresist. I also got to talk to experts and learn especially about one specialized window of engineering. It was not always easy. I faced a lot of setbacks. When I was reading these papers, it felt like I was like 10 years old again, trying to figure out what a common denominator was, like crying at the dinner table. It was not fun, but it also had its highs. I remember many times working with my coworkers after solving essentially a day-long problem of fiddling with this machine settings and how rewarding it felt when we finally made that breakthrough. If you remember one thing from my project, think about the quote I said earlier. Growth for the sake of growth is the ideology of the cancer cell. Science is what has doubled human life expectancy over the last 200 years, and it's how we know in precise detail how the world around us operates through science, through chemistry, through biology, and through physics. To keep continuing this trend of growth, there will be a cancerous growth sort of bloating either a journal or the workplace or even as a student. Let's try to create the conditions necessary in university research for great discoveries to be made again. Have purpose, be ambitious, and above all, try to compete.
Yes.